Hello there guys, welcome back to another epic inexorable maths video. In this video we're looking at a very special integral. We're looking at the integral from 0 to infinity of sine x over x dx. Okay, this is called the Dirichlet integral or the Dirichlet integral, and it's named after a mathematician by that name, but we're going to use Feynman's trick to do this. Okay, so I've already got some videos on Feynman's trick. Check them out if you would like to, or we can go straight in if you're feeling up to it. But let's have a look. So we're going to use Feynman's trick, as I say. Now, the thing is that in the previous videos that I've made on Feynman's trick, it's always been pretty clear how to kind of go about it, even though it's a bit trippy in a way. It's been fairly straightforward because there is already this made-up variable. There's normally an a in there already, or some random letter like a t or an a or a b, that we can differentiate the integral with respect to and then do stuff. Here it's like, well, where do you even start? Because there isn't an A, a T, a B, there's nothing there. So it is trial and error. Unfortunately, there is no way of knowing exactly what the parameter that we should introduce should be and where it should go and how it should behave, but we can just try things out. So intuitively, my thought process would be, if I'd never seen this before, I'm dividing by x and there is an x inside of the sine function. If I introduce a variable inside of the sine function and then I differentiate the integral, I can cancel it out. So my intuition would say I'm going to make up a function, maybe let's say f of a, to be the integral from 0 to infinity of sine of, let's say, ax over x dx. The reason that I would do this is because if I differentiate this function with respect to a, then the x would come out by the chain rule, and I'd have x cos ax over x dx. And this is nice because the x's cancel out. And we just get the integral from 0 to infinity of cos ax. Now, the integral of cos is fine, but the integral from 0 to infinity of cos, or of cos ax, is not fine, because this is a divergent integral. This does not have a finite value, so that we're at a dead end. We cannot do anything with this. Although this seems to be the intuitive way to start it, we realize it simply doesn't work. So unfortunately, as convenient as it may have seemed, we cannot do this. We need to come up with another substitution, another parameter, I should say, to allow us to use Feynman's trick. Now, what I'm about to do may not seem very intuitive, but when we go through the question, you'll see that it kind of makes sense. You are not really expected to just know how to come up with this. It's a clever thing, and once you know it, it makes sense, but you kind of do have to have seen it before, unless you're a genius. But really what I'm going to do is I'm going to say f of a is the integral from 0 to infinity of sine x over x times e to the minus ax dx. And I'm also just going to note that I want a to be positive, otherwise it would diverge. So you might say, well, that seems really random, but do you notice that f of 0 would give us the integral from 0 to infinity of sine x over x times e to the 0, but that bit is 1. So f of 0 is what we're looking for. So that's nice. Also, this integral, when we differentiate it, will still converge, which is better than the previous thing that we did. This is the logic, this is the thought process. It's not obvious why you would put an e to the minus ax there to, like, in your head before you come up with it, but now it's written down. Hopefully it kind of makes sense. Okay, so we're going to do this integral, or we're going to differentiate it and then do it. Okay, so the derivative of f of a is the integral from 0 to infinity. And remember, we're differentiating this thing with respect to a. So we're going to have a sine x over x, that's still there. That's a constant. And then when we differentiate e to the minus ax, remember, it's with respect to a. So a is the variable and x is a constant. So by the chain rule, we're going to get minus x e to the minus ax. Okay? I know that's crazy. Once again, this is really nice because the x's cancel out. That's kind of why we still did this, because it can still cancel the x out. It's just doing it in a different way. And then we can just do one more line here just to simplify it before we get into the real monstrous integration by parts stuff. Luckily, the integration by parts mess is the majority of the working out. So we have this integral, the integral from 0 to infinity of, and also there should be a minus sign there, minus sine x e to the minus ax dx, okay? Now, I'm going to do integration by parts to work out what that whole thing is, okay? So this bit is a little bit annoying, but I'm gonna do it, okay? So what I might do is put a time code in the video, just so if you wanna skip past all that working out, you can. But if you wanna stay with me while I do it, then you also can. So feel free to do that. Let's get into it. So I'm gonna, first of all, not worry about the minus sign, and I'm also not gonna worry about the limits either. I'm gonna do the indefinite integral. Actually, we can kind of stay on this, this blackboard for a second. So over here, I'm going to do the indefinite integral, and then I'll do all the limits and stuff at the end. I just want to work out what is the integral of, and again, I'm ignoring the minus sign, sine x e to the minus ax dx, using integration by parts. So you might know about this already. It's a pretty common question. So I'm going to say that u is sine x and dv dx is e to the minus ax. That means that du dx would be cosine x, and v would be minus 1 over a e to the minus ax. Hopefully that makes sense so far, which means that we can rewrite this integral as u times v, so minus 1 over a e to the minus ax times sine x, minus the integral of v times du dx. There's already a minus there, so I'm going to make that a plus. There's also a constant 1 over a that my fat head is in the way, but I'm going to take that out. And I've got the integral of just e to the minus ax cos x dx. Okay, just about have space there. Then I'm going to use integration by parts again on this guy here, okay? So I'm going to do this down here. Hopefully it's not too messy. But I'm going to say this time that u is cos x and dv dx is e to the minus ax. That means that du dx is minus sine x, and it means that v is minus 1 over a e to the minus ax. So that means that the integral of e to the minus ax times cos x dx is equal to u times v, so minus 1 over a e to the minus ax cos x, minus the integral of v times du dx again. Now there's two minuses here, so I don't need to take a minus out. The two minuses cancel themselves out, and there is still a minus there because that's in the formula for integration by parts. And it's just, but what I will do is take out this 1 over a again. So 1 over a times the integral of e to the minus ax times sine x dx. Okay. Now we can see that we have this like cyclical thing. If I just rename the integral of sine x e to the minus ax, if I just call this thing I, just for a second, just to make my life a bit easier, then we have that I is equal to minus 1 over a e to the minus ax sine x plus 1 over a times that integral, the integral of e to the minus ax cos x, which is minus 1 over a e to the minus ax cos x minus 1 over a times, and this is I again. And that's why I've done that. And then if we just rearrange this a little bit, then we get I equals minus 1 over a e to the minus ax sine x, and then we've got minus 1 over a squared e to the minus ax cos x, and then that's going to be minus 1 over a squared times I. If I add 1 over a squared times I to both sides, then I get I plus 1 over a squared I equals all of this stuff again. 1 over a e to the minus ax sine x minus 1 over a squared e to the minus ax cos x. And then there's several ways I can do this. I'm probably going to, just for the simplicity of it, I'm going to times both sides by a squared. So I'm going to get a squared I plus I equals a e to the minus ax sine x minus e to the minus ax cos x. Okay, then I'm going to move on to the next whiteboard or blackboard. I'm then going to factor the I out here. So I've got I times a squared plus 1 equals all that stuff again. And I'm also going to factor out an e to the minus ax from that. So I've got a sine x minus cos x there. Okay, there we are. And at this point, I think what's probably best is, well, we'll still divide both sides by a squared plus 1, that's fine. So I on its own is e to the minus ax over a squared plus 1 times a sine x minus cos x, like that. Now remember, that's I. I is the integral of sine x e to the minus ax. We want a slightly different thing. We want the integral from 0 to infinity of minus that. So first of all, let's just plug the limits in, the integral from 0 to infinity. That means that the integral from 0 to infinity of e to the minus ax sine x dx is this thing evaluated at 0 and infinity. Now, that means that I'm going to have to do a limit. So this is the limit as t approaches infinity of this whole thing. So e to the minus ax over a squared plus 1 times a sine x minus cos x, boom, boom, and the limits are 0 and infinity. Okay, cool. Yep, that's fine. Okay, continuing. We then have that this is equal to, and actually I'm going to make a bit more space, it's equal to the limit as t approaches infinity of, oh, and the whole point of putting a t, this is my mistake, whole point of putting a t over there is so there's a t there, I missed that. So that's a t, and then we just plug t in where x is. So e to the minus a t over a squared plus 1 times a sine t minus cos t. And make sure I've got the right number of brackets everywhere. Yep. Minus, and then we're plugging 0 in. So minus e to the 0 is 1, so 1 over a squared plus 1 times, and then this ends up just being 0 minus 1. So times minus 1 there. Again, making sure I've got the right number of brackets. Cool. Now, we can see as t goes to infinity, e to the minus at goes to 0. Sine t and cos t, they wiggle around, that's true, but they never exceed the number 1. So even at their biggest, they are the number 1, and it's timesing by basically 0. So this is 0 here, and then we have minus 1 over a squared plus 1 times another minus 1. So all in all, with all the minuses, pluses, and all that business, you get 1 over a squared plus 1. Now the final thing is, that is the integral from 0 to infinity of positive e to the minus ax sine x. What we have is minus this. So we now know that the derivative of f of a is minus 1 over a squared plus 1. And that's because This integral without the minus sign is positive 1 over a squared plus 1. So this is minus 1 over a squared plus 1 for that reason. Okay, that is the tricky bit done. Okay, so now I'm going to clear the board and we can continue. Okay guys, let's keep going. We're almost there. So we know the derivative of f of a is minus 1 over a squared plus 1. We can now integrate to get f of a. That's what we're looking for. We're technically looking, remember, because this is f of a here, we're technically looking for f of 0. That's what we want. But first of all, we need to know what f of a is in general. So we're going to integrate this function, okay? And I'll do it up here. So f of a would have to be the integral of the derivative of f of a, which is again minus 1 over a squared plus 1. So it's the integral of minus 1 over a squared plus 1 dA, okay? And this is a very famous integral. The integral of 1 over x squared plus 1 dx is arctan x. So there's no exception here just because it's the letter a. So this is equal to minus arctan or inverse tan of a plus c, okay? Cool. Now, in order to know what c is, just as in the previous videos, we need to know a bit of information about the original function. Now, there's no benefit here of knowing any finite values or plugging any finite values in, because we don't know what this integral is when a is, for example, 0. That's what we're looking for. But even when a is 1, when a is 2, when a is 3, we don't know any of these values. However, we do know that when a tends to infinity, then the inside of that integral gets closer and closer to 0, because e to the minus infinity times x is 0, and then it's timesing by this sine x over x, okay? So what I do know is that the limit as a approaches infinity of the integral from 0 to infinity of sine x over x times e to the minus ax dx, okay? I'm going to interchange the limit and the integral. Don't ask too many questions about it, guys. We can do it, but don't ask too many questions, okay? I'm going to interchange the limit and the integral to rewrite this as the integral from 0 to infinity of the limit as a approaches infinity of this thing here. I'm not actually going to write it, but just imagine it, just to save time. If I do this, if I take the limit of this function as a goes to infinity, do you see that that integral, the inside of it, becomes 0? So the value of the entire thing is 0, okay? So this is equal to 0, okay? But this is f of a. So that means, because this is also f of a, that means that the limit as a approaches infinity of minus arctan a plus c also has to be 0, because they are alternative definitions of the same thing. So of course the limit must be the same for both of these two things. They're both f of a, so that's why they're both 0. Now, the limit as a approaches infinity of arctan of a is a very well-known result. It's pi over 2. I'll explain that in a second, okay? So this is minus pi over 2 plus c, and we know that's equal to 0. Now, just a really, really quick mentioning of why is the limit as a approaches infinity of arctan a equal to pi over 2. If you draw the graph of tan, this is pi over 2, this is, I'll just do it with x, okay? This is tan x, just on the interval between 0 and pi over 2, and you have an asymptote here. Remember, the inverse of a function is just a reflection in the line y equals x. So the graph of arctan looks like this, and so there must be a horizontal asymptote at pi over 2. So you can see that as x gets bigger and bigger and bigger and bigger, arctan of x gets closer and closer asymptotically to pi over 2. That's why we know that is true. And of course, we can see that c is pi over 2. Okay? And that means that the final definition of f of a is that f of a is minus arctan of a plus pi over 2. Or in other words, pi over 2 minus arctan of a. obviously they're the same thing. Okay, now technically we can work out any value of f of a that we want, but we're interested in f of 0. Again, f of 0 is when we have the integral from 0 to infinity of sine x over x times e to the 0 times 1. That's what we're looking for. So all we need now is f of 0. And guys, it's super easy. F of 0 is pi over 2 minus arctan of 0. But arctan of 0 is 0. And again, you could even refer to the same graph. But arctan of 0 is 0. And so we get pi over 2 as our final answer, which means that the Dirichlet integral, the integral from 0 to infinity of sine x over x, is actually pi over 2. And that's how it's done. Thank you guys so much for watching. I highly appreciate it. And I'll see you in the next video. Cheers.